All right, so let's now learn about exponential functions. The whole idea of an exponential function starts out by first, let me bring up an example of a few computational problems as following. So let's say I have a base 2 and I want to raise that to the power 3, for example. And so in the way how I see this now, 2 is the base and 3 is the exponent. But so the calculation can come out pretty easy, and we can easily find that with the calculator here. So on the standard TI-83 and 84 calculator, we just go 2 and raise power with that key right here, the hat key, and then power 3. And the answer is now 8. So 2 to the third power equals 8. And remaining with the same base, I am going to bring up another calculation. So what about a 0? So I'm still going to remain with same base 2. 2 to the 0 is algebraically known to be 1. And we can verify that with the calculator. 2 raised to the power 0 equals 1. And now, again, remaining with the same base, positive 2. I am now going to raise to a power, how about negative 4, for example. And so on the calculator, we can quickly perform a value here. 2 raised to the power negative 4. And the answer now is 0.0625. 0.0625. Now, the calculator gave this value in decimal, but we can also know that with some algebraic property, we can also be acknowledged of the fact that 2 to the negative 4 is equal to 1 over 2 to the 4th power. And 2 to the 4th power is 2 times 2 times 2 times 2, which is 1 over 16. And so these two answers are supposedly equal value. And then, so far on the same base 2 right here, and notice the base I'm using here is a value, well, 2 here is a number, but positive value. Now, I can also bring up another quick computation. How about base 2 again, but being raised to a power, how about a 1.5 power? A 1.5 power. Now, with this one right here, it's really beyond our mental math capability, so we definitely need to use the calculator. Now, any of us here viewing the video, any of the viewers viewing my video so far, I don't need to swing by the calculator for any of these calculations. We can easily do this through the mental math. But the reason I show the calculator is for anyone to get comfortable with how we can use the calculator. But so now when it gets to a calculation like this, 2 raised to the 1.5 power, then it's beyond our mental math capability. We can go ahead and use the calculator. And again, on the calculator, 2 raised to the 1.5 power is a value quite complicated and quite lengthy in decimal. And so in 3 decimals, it's about 0.828. And so now, upon successfully completing a few computational problems where we are based on base 2 here, then it looks like all of these computations bring us into a function as following. It's a function 2 with base 2, but raised to exponents being x right here. So we can see that if we define now a function f of x to equals base 2 raised to the x power, then 2 to the 1.5 is the same as f of 1.5. 2 to the negative 4th power is the same as f at -4. Once we define this function, once we recognize that we're having a function 2 to the x, or 2 to the 0 is once we're seeing this as a function 2 to the x, then 2 to the 0 is the same as f at 0. And this value here is the same as f of 3. And so a function defined like this, where we have a base and the variable is being put in the exponents form right here. This function is a basic exponential function. So what we have here is an exponential function. Okay, and more specifically, base 2 in this case. And I also emphasized this little detail here, that the base we're using in here is a positive value, to get anyone into that track of formally defining what an exponential function is. All right, and so now we are ready for a formal definition of what a basic exponential function is. So I'm going to say a function f of x given by f of x equals a base a raised to the x power. So a function like that is called an exponential function. And to be more precise, this is regarded as the basic exponential function. I am going to come back to this definition and put in some more details into that. But let's now look at a few things right here. So now, let's say we pick a number, positive 2, and raise that to the x power. We have an exponential function, and we call this exponential function base 2. Let's say we pick a value being a positive 5 and raise that to a power x. This here is an exponential function of base 5. Now, exponential functions are not only limited to whole values to be the base. We can use a 1.5 to the x. That's entirely fine to be an exponential function. We can use a very ugly looking decimal value such as the pi and raise that to the x. Pi to the x is an exponential function, just fine. But now a few functions that are mistakenly recognized as exponential function, but it turns out they are not. How about a -3 raised to the x? This is not, I put a cross away indicating that this should not be recognized as an exponential function. So not an exponential function. Now, x to the third power, for example, this is not an exponential function. So this one here is not an exponential function because base is -3, and that's less than 0. And as I highlighted earlier, even though I did not put that in the formal definition yet, but in order to be an exponential function, the base can be a decimal, but they must be the bases must be positive value. And here we're looking at a negative base, so that function here cannot be an exponential function. this function here is clearly not an exponential function. This function is precisely a power function. Simply because let's have a closer look at the way how this is compared to 3 to the x. Now 3 to the x is an exponential function, base positive 3, and the variable x is being placed in the exponent part. Whereas here in this function, I call that it's a power function because the variable is being raised to a fixed power. Here it's a variable power. This is a constant fixed power. The base is the value that's being changed depending on the value of the variable. So this function here is called a power function instead of being an exponential function. And so now back to the formal definition. A function given by this form right here is called an exponential function, and as a matter of fact, a basic exponential function, where the requirement here is the base a must be a positive value. And so back in the formal definition, a function f of x being defined in this way, a base a raised to a power x right here is called an exponential function. And as a matter of fact, a basic, and that's why I put basic here in parentheses, a basic exponential function under the requirements that, so I'm going to say where the base a is strictly required to be a positive value. All right, so now let's look at a couple examples of exponential functions so that we can determine if a function can be formally a basic exponential function or not. And of course, I have already shown a few examples, but here I would like to formalize all of these examples because they are more into recognizing an exponential function. So we want to determine if the given function is an exponential function. And so I can come up with part A of this current example, a function f of x to be 1/2 in parentheses raised to the x. So we want to find out if this function can qualify to be an exponential function. So all I need to see is to look at the base here. So the base we have here is a 1/2 base, and it's already itself a positive value. And even though being written as a fraction, but in the end 1/2, all it needs is a positive value. And so with this base here, well qualifying to be meeting the requirement, so this function is an exponential function. In a different question, we can look at a function 10.758, a really crazy looking decimal, but raised to a power x. Can this be an exponential function? Again, what I see here is the base being raised, the base itself, even though not a whole number, but in the end it's a positive value. And so this function is an exponential function. In another example, our function can be f of x equals 0.25 to the x. So 0.25 is a value in decimal, And the base, the way how I see the base here, in the end, it's still a positive value, even though it's not a whole value. And so this function is an exponential function. In another example, now I had pointed this out earlier, and it's worth it to mention again. A function like this, -5 with a base and raise the base to the x. So calculation to this function could be something like -5 to the 4th power, -5 to the -2 power, and -5 to the 0 power. So we can perform the power operation here. So -5 here is the same as to the 4th here, means -5 times -5 times -5 and times -5. And whichever the answer that would come out, we will have an answer. Now this here is the same as 1 algebraically 1 over -5 square, and we can still perform the operation. -5 times -5 in the denominator, and we will get an answer, 1 over 25. And this here will give us a 1, because any value, any non-zero value raised to a power 0 is going to equal 1. But due to the fact that the base here, in the end, the base we're looking at here, the value -5 acting as the base, is less than 0, being negative. So this function is not considered. So it's not considered as an exponential function based on the definition of our exponential function. Now I am going to look at another question in my example here. Let's say 3 to the x, but we have a 2 times here in front. So this function, the way I see that, and notice according to the order of operation, then once we're substituting in a value for the variable, for example 3, then this function, the way to evaluate that is going to give me 3 to the 3rd power, because here's according to order of operation we have to raise a power or exponents before multiplication, because always anytime anyone proceeding into an operation, record for yourself PEMDAS. So P stands for anything that's inside parentheses must be taken care as at the highest priority, and then after that it comes to exponents, and then multiplication and division comes after exponents. And so here we have a mix between raising power, raising exponents, and product. And so that means when we're substituting in 3 into the function, then we have to raise power to the 3rd power, and this 3rd power is the value we have given for our function variable. And then after that we multiply with 2. And so in the way how I see, then doing it this way, I can still see that this is the exponential function. It has the exponential function part. And so what is that 2 doing here? That 2, of course, comes after we raise the exponents. So that 2 here is being now regarded as, and by the way, this calculation here turned out being, so it's a 27 times 2, so 54. But in the end, this 2 that we can place in front of the exponential function. So I pointed out this part right here is exponential function, but the 2 in front is now just simply acting as a coefficient. All right, and so having a coefficient is okay for being an exponential function. So in other words, our function here, after so much note of mine, now let me rewrite it. A 2 times 3 to the x, a function like this, is also an exponential function. We will actually, after we go through some more properties, including graphical properties of an exponential function, and I will get to explaining how this function here can, how we can extend our general understanding of exponential function into a more general format of the entire family of exponential functions. So just for now, this function right here, we have an exponential function, base 3, and multiply with the coefficient. This is well qualified to be an exponential function. And so right out from that explanation I have just explained, then let's look at another problem right here. How about f of x, another function here, negative 5 to the x. Now, unlike the one I brought up earlier, negative 5 in parentheses raised to the x, this is base negative 5 and raised to the x. And so we already agreed that it's not an exponential function. But here, indeed, connecting with the problem with the part E that we have just finished, then the way I see this function here is indeed base 5 raised to the x. And what explains for the negative sign? It means a negative 1 times 5 to the x. And so now I see this as the negative 1 here, or just simply for short, the negative sign, it's just the coefficient. So it's the coefficient. And this part right here is our exponential. All right, so in this way, a function like this is indeed very unlike with the one negative 5 in parentheses raised to the x. This one here is well qualifying to be an exponential function. And another one I can point out, we can have a function f of x, and we treat the base as a 0 and raise that to the x. Okay, so as far as doing the operation, yes, we can do 0 to the first power, which gives me a 0, because 0 times it's 0 itself. 0 squared is 0 times 0, which is 0, and then all that. But as far as being classified, as far as being classified as an exponential function, then this function does not belong to the family of exponential function, not at all, simply because the base here equals 0. That base that we're looking at equal to 0, where we require the basis to be a positive number. In this video lesson, we are going to study the graph of an exponential function. But even so, this video lesson is prepared and aimed at students, viewers who are in math courses on track for those professions or careers that are not so heavily math related, such as business field, economy, social and health sciences. And throughout the entire lesson here, I am going to be using many technologies that can effectively help in creating graphs of an exponential function. So those technologies are the standard TI-83 or 84 calculator, and I'm also using along the way with the graphing calculator Desmos.com. That can be found at Desmos.com. All right, so let's start out having our first look at the first graph of an exponential function by investigating the function 2 to the x right here. And so I will be brief on the idea of table of values, because fundamentally speaking, anytime we're investigating or studying the graph of a completely brand new function, then we need to start out from the idea of constructing the table of values. However, we can go brief here. So let's say I'm now looking at studying the graph for this function, specifically 2 to the x. It's an exponential function with base 2, positive base 2, and being raised to the x power. And so now with Desmos, I can provide a table of values, and Desmos can do a quick calculation for me. But I will also clarify along the way with the TI-83 or 84 calculators. So let's say in my, just like the usual table of values right here, my left column right here is the column that's getting ready for me to put in the x values, the independent x values, and the right hand side column on my table right here is the automatically calculated y value that's supposedly the output for our function f of x, which is in this case 2 to the x. So I am starting out by giving x inputs to be 3. And so Decimal can quickly calculate the y value outputs, or the output of f of 3 to be 8. And immediately we notice in the graphing area here, there's a point that says 3, 8, which is 3 for x value and 8 for the y value. And so that is how convenient decimals can do for us in terms of quickly generating a table of value. However, to make sure students who are viewing this video to understand where this value comes from, allow me to quickly show the actual calculation on the TI-83 and 84 calculators for a few input values. So if we would like to achieve 2 to the third power, this is how we can get it done on the calculator. 2 raised to the third power. And then now hit enter. And that quickly gives us the final output. So this is f of 3 right here. So 2 to the third power. And so now back on my Decimals graphing calculator, let's look at giving a different input value. So I purposely started out with giving the inputs being a positive value. So positive 3 I gave for x, and I came out with output 8. So let's look at a value, how about 0? And we want to find out whether an exponential function can be evaluated at x equals 0. And so there we go. We immediately had the table gave us y equals 1 when x equals 0 given. That means 2 to the 0 power equals 1. Or we can quickly see this on the calculator that our function is base 2. Now we raise to power 0, and that gives us 1. And so how about a different input value? So on my table here for the x value, I am now going to give, how about a negative value? And so far you can see that when x equals 0, we have a point down here being 0, 1. And when x equals 3, we had a point 3, 8. So it seems like from the left to the right, our graph is expected to rise. But let's find out further. So now I am giving it, how about negative 3 as an input? Okay, so negative 3 as an input. Decimals is only showing in decimal, 0.125. So at this point, I strictly need to clarify here. So really, when we're inputting x equals negative 3 into the function, f of negative 3 means 2 to the negative 3 power, or 2 to the negative third power. Let's see how the calculation can be done on the calculator. So on the actual calculation, which decimals already had the answer, but we just want to have a sense about some verification. And in a later, once anyone viewing the video has a good hang of it, then in a later problem, I won't have to be as detailed as right now. So here we go, 2 raised to the, so for negative signs, negative 3. And there we go. So 2 raised to negative 3 is a 0.125. Another way of seeing is 0.125 is indeed the same as a 1/8. So 2 to the negative 3 is also the same as a 1/8. And so now if we're looking back at our computer screen right here, we can see that with the 3 points being placed on the graphing area right here, the first, and after we particularly placing these points in the increasing order on the x-axis here, so negative 3, 0.125 is the far left one, and then it comes 0 as the next one, and it comes to 3 to the right hand side, as I said, in increasing order from the left to the right on the x-axis. Then we can notice that our 3 scatter points so far is forming into a rising path. But notice how this rising path is not a linearly rising path. And so for that reason, let's put in more x values here so that we can get a better refinement and recognize a better shape of our graph right here. So for that reason, now I am going to get on this table again. And now let's put in x equals, how about x equals 1 here, and let's find out what the output value is. And starting at this point, I don't need to I no longer need to swing back to the graphing calculator TI-83 or 84 any longer, because anyone, if you are doing this, you are following along with this video, you can pause the video now at any moment to do your own calculation to get yourself convinced how Desmos gave me these output values correspondingly. So how about when x equals 1? We have an output being 2, and that correspondingly gave us a coordinate pair of values. And now we treat that as a point on the graph here, 1, 2. And now how about when x equals 2? We can have another point here, being 2 for x and 4 for y as the output. And consequently, we ended up with another coordinates pair of values here, being 2, 4, and represented as a point on the plane. And how about let's put in some other negative values between 0 and 3 as we've had earlier. So now how about negative 1? And now we Desmos quickly gave us a 0.5, which is right here. The point was already being placed on the graphing area. And how about one more value? So now how about negative 2? And so when x equals negative 2, our value quickly became 0.25. And now that we already formed into a better refinement of our path here in terms of these, the shape that these scatter points form right here, then it's now time to actually review the actual graph of our 2 to the x function. All right, so here we go. Now Desmos can quickly bring up the actual graph in red line right here. So it's not a straight line, but it's a curve being in red color. But so now this curve right here is the graph for our function 2 to the x. So that is the graph of our first exponential function, base 2 raised to the x power. And so let's have a good observation of this graph before we start moving out and investigating other graphs on other exponential functions. And you can see how these points that we plot out from the table of values are perfectly placed on the graph right here. Okay, so the way how I see it right now, this graph is a rising graph and rising in one way, meaning from the left to the right. From the left to the right, the graph is rising one way. And for now, we are particularly studying the graph of the exponential function 2 to the x, where our base of this exponential function here is a value that is positive, of course, but also greater than 1. So for our function f of x equals 2 to the x, our base here is a value that is greater than 1. And so again, notice how the shape of our current function is the shape that's currently rising as a one-way bent curve, but rising from the left to the right. Okay. So now let's use my favorite Desmos graphing calculator to put in the graph and study the graphs of a few other exponential functions, so that we can start drawing out some generalizations right here. So first of all, our function that we have seen earlier, 2 to the x, is right here, where the graph is in the red line right there. And it was that same curve rising from the left to the right. It crosses through the y-axis. And now I have to mention that back at the earlier part of this video, that when I was explaining what an exponential function is, then as long as we have a value, a numerical value being a positive value, then that value can just be entirely fine to be used as the base of an exponential function. So in other words, what I'm trying to say now is that for a function such as 2.4 to the x, as on my list being written right here, it is entirely an exponential function. And again, the way how I'm seeing it, it's a positive value, and it's also a value for now being greater than 1. So let's now quickly bring up the graph for this function 2.4 to the x right here. So here now we have the graph for 2.4 to the x, where the base of this exponential function is slightly larger than the base 2 to the x. And the graph now is in blue shape right here. But so far, with the two graphs being blended together, we notice there is still the similar fundamental shape right here. And of course, I will bring up more common properties among all of these functions. And so further, again, let's look at the graph for our function 3 to the x here on the list. So 3 now is a positive value and a value greater than 1. And so far I've been bringing up exponential functions where base is greater than 1. And so now 3 to the x. Let's now bring up the graph here. And this time the graph is being displayed in green color. So let me now put in some closer zoom right here. So with the graph for 3 to the x being displayed in green color, the green graph is right here. Okay, so the green graph is here. And again, it's still that same fundamental shape that's going one way, rising from the left to the right. And then so far throughout all the three graphs, the one common thing we notice now is that as the graphs passes the y-axis, then the rising becomes more rapidly compared to the left-hand side. Let me now temporarily hide away the two graphs in green and blue here. And let's look back at our 2 to the x that we have seen. So it's rising. It's going one way, but the rise on the left-hand side, the amount of rising to the left-hand side of the y-axis here is slow, meaning slow rising. But then as we go past the y-axis, then the rising becomes a lot more rapidly. So the same way now with the graph in blue for 2.4 to the x. With our graph right here being in blue, once again, if we now turn our focus to the blue graph, then the rising, once again, it's a one-way rising from the left to the right. The graph keeps rising up, and the amount of rising becomes rapid as we go past the y-axis. And now looks like it's going to be the same way with the function 3 to the x, where the graph here is displayed in green right there. And the rising is slow, but particularly growing fast. So it's growing fast and rising fast, rapidly fast, when the graph gets to the right-hand side of our y-axis. And so even further, let's now look at the graph for the 5 to the x right here. So 5 to the x is now the graph being put in purple color. So now let me highlight the graph there. So now with the graph in purple color, so 4 graphs being displayed so far, and our 5 to the x is in purple color. But in the end, once again, the same fundamental shapes, rising one way, going one way from the left to the right, rising higher. And again, the rising was slow, but as the graph passes through and pass to the right-hand side of our y-axis, then the rising amount becomes rapid and rapid. Okay, and so now after looking at all 4 different graphs in 4 different colors right here, we can start formulating a general pattern right here. So on my list here, I also purposely put these exponential functions in increasing order of the base. So from top down right here, our base here was 2 to the x, then 2.4 is slightly higher, then 3 is getting bigger, and 5 is getting bigger. And so 2 to the x started out with the red color. So, but at least compare with the 4 exponential functions here, and with increasing bases, then we can see that the curve becomes more tied in, become more rapidly growing. Or in other words, as we reducing the base, as the base gets smaller, then the curve becomes more flattened out, widen out. Okay? But in the end, it's all the fundamental shape that's rising from the left to the right in one way right there. And so now in that way, we can now, if we look back at our function 1.5 to the x, which I never show or display the graph before, we can now, before seeing the graph, we can already have a quick expectation that this graph here this function here being an exponential function, but having the least base amount compared with any of these other bases right here. So this is so far the least base. So I am expecting that the graph for this is going to be the similar fundamental shape right here, but must be a lot more flattened out compared to any of these bases here. So look at our red right here. It's going this way. So the 1.5 to the x, before I'm bringing up the actual graph, then I'm expecting that it's going further widen out like that. Okay, and so now let's really show the graph for 1.5 to the x. And so in that way, 1.5 to the x being displayed in orange color right here, then yes, just as I was explaining earlier, I was expecting that the graph for 1.5 to the x, still that same shape rising one way from the left to the right, but now a lot more flattened out. And so the rule of thumb, now we can see that as we keep reducing and you can see that I'm reducing these bases here so that it gets closer and closer to 1 like that. And so as I'm reducing the base to be closer to 1 for the bases, then the graphs keep getting more widened out and widened out. So now think of a further impact right here. If now I'm going to put in 1 to the x, it's entirely a legal exponential function, 1 to the x. But now 1 to the x here, let's look at the graph right here. Of course, I am expecting that the graph is going to be even more flattened out compared to 1.5 to the x here. But then let's really look at that. Now we have a completely flat line. So the line in black right here is the line for our exponential function, 1 to the x. So a little bit of an algebraic explanation. The reason that we have a flat graph is simply because when our function is a 1 to the x, when an exponential function is with base 1, then 1 raised to a power 2 equals 1. 1 raised to a power negative 3 equals 1. And 1 raised to any power, even to the power 0, is a value 1. And that is the reason why all output values remains 1. And that is the reason why, and that's what explains for 1 to the x as now being explained as an exponential function, but has the graph being a completely straight, flattened horizontal line, being in black here as shown in the graphing area. And now let's look even further. So I have now displayed the graphs of 6 different exponential functions. And one further thing to be recognized that's common throughout all exponential functions. And for now, it looks like I'm intentionally working with all of those exponential functions where base is greater than 1. And so look at this point right here, the y-intercept. So any of our graphs of an exponential function, of the basic exponential function a to the x, passes through the y-axis right at the point 0, 1. So for now, let's look at the purple one for 5 to the x. So it passes through 0, 1, or it has the y-intercept right at this point right here. Y equals 1 right on the y-axis. The orange one for 1.5 to the x. The orange one also passes through 0, 1. 0 for x, 1 for y. And our function that we have seen from the very beginning of our discussion, 2 to the x, is right here. This curve in red also passes through the y-axis at y equals 1 on the y-axis, or completely as a value, as a coordinates point, 0, 1. And so the same with any other graphic there. And so now that is good enough for us here to draw out some generalizations about the graph for a basic exponential function, y equals a to the x. But particularly we're looking at the case where our base is a value greater than 1. And of course, needless to mention, any base that we're using for an exponential function must be a value positive, being positive. So the generalization that we can see now, that we can draw out now, is that as long as our base is a value greater than 1, then the graph will commonly be a graph that's going one way, bending up and rising that way. So now when we are completely leave the worry about scaling, then generally speaking, what comes in your mind about the shape of an a to the x when base a is greater than 1 is that it's a shape, it's a bent curve that's rising one way from the left to the right. The rising is slow on to the left hand side of the y-axis, but becomes more rapidly rising when it's go to the right hand side of the y-axis. And any exponential function a to the x, and for now we focus our study on for base greater than 1, then it looks so far that all exponential function with base greater than 1 passes through any of those exponential function with base greater than 1 passes through that point 0, 1. And now let's see how our TI-83, 84, or generally any graphing calculator can be useful for us in terms of getting our own exponential function graph. So I am particularly showing viewers how to create the graphs of an exponential function with base greater than 1 on the TI-83 and 84 calculator. But for viewers of this video that use a different calculator other than the TI families, I am confident that your calculator will also have the similar function that can draw the graph of any exponential function as well. So to draw the graph of our exponential function, we must first enter the function. So click on y equals, and then now I am going to type. Now we're looking at, let's start out with let's just quickly do base 2. So 2 hat key is for raised power, so 2 to the x. But now as the x variable on the TI calculators, the variable is being located right here. Okay, and so now we hit enter to exit out of that line right there. So now we have entered our function y1 is to be 2 to the x. Now the software I'm using here, the emulation software I'm using here for TI-84 calculator is quite recent, and so it even has the fancy feature that it color codes our different graphs. But in case you have older versions of your TI calculators, that shouldn't be a big problem at all, because color coding is not the main it's not the main aim that we're looking at. But now once we have entered our exponential function here, let's see what it looks like. So for simplest way to get there, simply click on graph after we enter our function, and so there it is. That's the graph for our 2 to the x. And of course, on standard, this is the standard zoom with the TI calculator. It's not exactly the square scale, and you can see that this is a scale of 1, but this is the scale of 1 on the y-axis, and this is the scale of 1 on the x-axis. So anyone here, you can read your manual to click on the zoom to adjust the different zoom type right here. But I'm going to leave that for users to explore your own calculator. And so that was the graph of our 2 to the x function, and once again it goes through that point at 0, 1 on the y-axis. And just like what we have already recognized, then this is a one-way graph that's rising from the left to the right. The rising amount is slow when it was still on the left-hand side of the y-axis, but becomes rapidly quick. It becomes rapid when it gets to the right-hand side of the y-axis. All right, and now let's look at the graph of an exponential function that base a is a value that is, of course, still positive, but less than 1. And so now I am specifically going to focus or paying attention to base a positive, but less than 1. So a quick example, and also an example that deserves some good starting attention, could be, let's say, 1/2. 1/2 is a value that in decimal expression, it's a 0.5 in decimal. So let's look at 1/2 to the x, or that is equal to 0.5 to the x. Y equals. So let's look at a function like that. And so our base here, 1/2, is a value that is, of course, greater than 0. But in our case right here, specifically less than 1. So I am going to use decimals again to graph. And when we're getting on decimals right here, and of course, at this point right here, I assume that any viewer is flexible enough to understand, to be able to understand interchangeably the two different forms, the two different expressions of a value, either in fraction or in decimal. So now on my decimals graphing calculator, so here I have prepared our function f of x to be 0.5 to the x. So this is the same way of the same thing as 1/2 in parentheses to the x. And so let's quickly use decimal to build a table of values. And as you have had some experience throughout our earlier graphs right there, so now I can start picking up pace a little bit here. But let's try out with a positive value, because now, as we know, that an exponential function can take a positive value. So let's say positive 3. Then it will give us an output value y equals 0.125. And you have already seen earlier how you can use your standard calculator, either a TI 83 or 84, or any basic calculator can help you do this calculation to verify the output value that was already calculated here by decimals. And so now there's no need to swing back and forth with the calculator there. So we can input a value independently for x equals 0, for example. And decimal quickly came up with y equals 1. And of course, now at this point, you can use your calculator to verify this calculation, that 0.5 to the 0 power equals 1. And then for the next value, we can quickly try the -3, for example. And so now after 3 coordinates points being placed on the graph right here, then let's purposely look at all these 3 points. Let's look at all these 3 points in the increasing order from the left to the right on the x-axis here. Then you can see that our first point, -3, 8, corresponding to this pair of values, -3 for x and 8 for y. This point is the first point in our graph on the left right here. Then 0, 1 is this point right here, corresponding to this pair of values. And then the 3, 0.125 is corresponding to the last pair. So if we're looking at these points from the left to the right, then we're still looking at some kind of curve. It's not a linear path, but it's a curve that looks kind of bent. But now let's put in more x value so that we can formulate a better refinement. We can come up with a better refinement of our, so that to make it easier to recognize the shape of our graph here. So how about I'll put in -2. And so the calculation from decimals came out with y equals 4. And that's how we got this point being placed on our graphing area. And now the shape is being better recognized and better recognized. But of course, I am still going to put in some more points right here. So how about -1? And so with -1, we have output value being 2. And then of course you can use your calculator, your own calculator, to verify all these results right here. So this is the point that's corresponding to -1 for x and 2 for y. And now I'm close to getting what I need to see in terms of the shape of the graph. But let's put in some more points right here, some more x values, so that we can create more coordinates points. So how about x equals 1? And so now our output value calculated by decimal is 0.5. And so that's consequently giving us a point right here at 1, 0.5 on the coordinates plane. And how about x equals 2? And so now I can see that the decimals gave us 0.25 for the output value right here. And consequently, we ended up with a points being placed on the graphing area here on the grid here on the graphing plane here at 2, 0.25. Okay, so now with all these points, again looking at all these points from the left to the right, with and what I mean is that we put all these points, we're looking at these points in the increasing order of the x values. Then we notice it forms into a path, and clearly speaking, this is a path that's bent. But now, unlike the case of the 2 to the x, this time now, since our base is a value that's being positive, of course, but less than 1, then it looks like we have a graph that's going one way again. That's these points formulate a path that's going down and going one way again, keep falling and falling and falling in a bent curve. All right, so let's now really put the actual graph of 0.5 or 1/2 to the x in the same graphing space here. And now the graph in red right here, that is the graph for our exponential function, 0.5 to the x. And so this time, unlike what we have seen earlier with a base being greater than 1, now when our base is less than 1, then the graph, the exponential function, becomes a curve that's going one way again, from the left to the right, but it's a falling graph. It's falling from the left to the right. And so right now specifically we are looking at our function 1/2 to the x or 0.5 to the x. All right, and so now before we can have a better generalization of what the graphs here give, let's now put our graph of 0.5 to the x together with some other exponential function. So right now here's our graph of 0.5 to the x or 1/2 to the x. This is that graph we have just seen, but let's put that together with an ask Desmo, and we don't need to use a table of values here, but let's ask Desmo to quickly bring up the graph for a few other exponential functions where the bases here are all being positive, of course, but less than 1, so that we can study some further properties, and as well as drawing out some common property and a certain pattern of how these graphs behave right here. Okay, so now starting out with 0.5 that we have already seen. So, and here's the graph of 0.5 being in red ink. Now I am going to use a different value here, still less than 1, but a little bit greater than 0.5 right here. So 0.75, or as a fraction, as a ratio, this is a 3/4. So you can think of this as a 3/4 all raised to the x power. 0.75 to the x is the same as 3/4 to the x. Those two are essentially the same function. And so now on our graphing calculator here with Desmos, I'm going to quickly put on the graphs here, and the graph for 0.75 to the x is being displayed in blue. So this blue curve right here is our graph for 0.75 to the x. And so with two graphs now being currently displayed on our exponential functions with base less than 1, then we are starting to see a common property right here. And the graph in blue here is also going one way from the left to the right, that's falling lower and falling lower. Okay, but let's not rush. Let's study a little further. So on my list here, I also have placed down a function 4/5 to the x. And now let's look at 4/5 to the x right here. 4/5 as a fraction will equal to 0.8 in decimal. So 4/5 to the x is the same as the exponential function 0.8 to the x. And clearly speaking, so 4/5 now is a base that's less than 1. So we already have some expectation of what the graph should be for this function 4/5 to the x. So now let's look back at the graphing calculator on Desmos right here. So now as I bring up the actual graph for 4/5 to the x right here, the graph is being displayed in green color, and you can see that it's doing that similar property right here. It has that similar shape that the two earlier functions have already displayed right here. It's a one-way falling graph from the left to the right right here. Okay, and so now 0.9 right here is even higher value, because So as in the way how anyone can see and understand my intention is that I purposely put these exponential functions in the order of increasing base values. So 0.5 so far at start, but 0.75 became a little higher, and then 0.8 or 4/5 here is even a little higher, and then 0.9 is going to be even greater. So now let's bring up the graph for 0.9 to the x right here. All right, so 0.9 to the x in purple over here, and that's the curve. And again, it's a one-way graph keep getting lower and lower from the left to the right. Okay, and so now at this point, after seeing the graphs of 4 different exponential functions where base is less than 1, and I as I have explained earlier, I put these in increasing order of the base, even though these are all less than 1. Then we can see that as our base value gets closer, because I started out with 0.5 for any one of us here to investigate, but as our base value keeps getting larger and getting closer to 1, then look at what happens. So in here it's our red, and when we move to the blue one, it becomes more widened out or more flattened out. And then when it comes to the green version where the base is even closer to 1, it's 0.8 here. It's higher than any of these base, but it's still less than 1. So of course it's closer to 1. And the graph in green here is even more flattened out. It's the most flattened out compared with these 3 graphs here before I put up the purple. And then when it comes to the purple, then 0.9 is even closer to 1 than any of these other bases. And then so this graph for the exponential function 0.9 to the x is even more flattened out and more flattened out. So now again, make a good prediction. That again explains that when we actually hit 1 to the x, where this base here hits to equals 1, then we have our graph completely, the graph on this line here on this exponential function completely flats out as a horizontal line here. All right, so if we're going back on the order here, if we're going backward, where we keep getting our base becoming less and less and less, so have a good expectation of this. What can we expect about the graph of this, the shape of the graph of this 0.1 to the x right here? So I am expecting that this 0.1 to the x must have a graph that's a lot more narrower. And so now here we go. So now the graph in orange being displayed, it's the shape that's still falling from the left to the right. Okay, and it's a lot more pressed in, a lot more rapidly fall here. Okay, and so now after seeing all 6 different graphs here, again we can also see another common property that all of these graphs has the y, any of these graphs right here has the y-intercept at that common point 0, 1. So let's look at the one in orange right here. The orange graph 0.1 to the x passes through the y-axis at 0, 1, or exactly at the y equals 1 on the y-axis. Then 0.5 to the x, we have seen that in our initial graph with the table, and now here it is together with the other graphs. Then it's a one-way graph pointing from the left to the, going down from the left to the right, and it passes through the y-axis at 0, 1, or y equals 1 right on the y-axis. And then the same with the blue graph right here, and the same with the green graph. They're all going through that point 0, 1. These graphs are all going through that point 0, 1. And now as these graphs for exponential functions with base less than 1 are all displayed here, then you can see that the fall of the graph was rapid before it hits the y-axis, but becomes a lot more slowly after it passes the y-axis and goes to the right-hand side of the y-axis. And that's still trivial for the other ones. So let's look at our 0.5 to the x right here. The fall was quite rapid, but then as we go past that point 0, 1 on the y-axis, the fall becomes less and less rapid right here, or it's a slow fall. But then that becomes less obvious with these blue and green graphs like that. Okay, so for example, this green graph, we can still see some quick fall, but as the graph goes past the point 0, 1, then the fall becomes really slowly or almost flat out, to the right hand side of the y-axis. Then 0.9 right here is so close to a horizontal line, and then when it comes to 1 to the x, it's completely flat out. We don't even notice any change or any fall at all. Alright, and so now let's get back on our writing board right here, on my writing board, and at this point we are ready for formulating a general, some generalization for the graph of an exponential function a to the x with base a being less than 1. So throughout all the graphs we have observed so far, then when the base a is a value less than 1, then any of our graph will be a one-way graph from the left to the right, but carry this common shape right here. It's a falling graph from the left to the right. And it becomes more steep. The fall is more rapid. On the left-hand side of the y-axis, and the fall becomes slow and more slowly to the right-hand side of the y-axis. So there's the y-axis here, and there's the x-axis here. And in any case, in any of the graphs, our basic function a to the x passes through that common point 0, 1. And so now as another piece of information that is good for anyone to know over here. So let me now put the two different cases when a is greater than 1, and the case of the graph where a is less than 1. Then when base a is greater than 1, our graph was going up from the left to the right. But now notice, if we look back at this form right here, the graph never sink below. So I use that term sink below, means the graph itself will never go below the x-axis. So in other way of saying that exponential function in this case, and we can graphically explain that the value, the y value is always positive. I'm talking about the y value will always remain positive, not even touching the x-axis. And then same way, we have now just investigated all of those exponential functions where the base is a value less than 1, and the graph become like this. It was a falling graph passing through the y-axis at 0, 1, and the same with this case right here. But again, doesn't matter how far we extend our x value, the graph itself vertically will never go below the x-axis. So again, the y value being defined as a to the x is always positive. And this is the reason why we can say that now when I was constructing table, then I was saying that for any exponential function, then we can take any input value, positive value, negative value, and 0 value. So domains, meaning possible x input values that we can use, that we can substitute into the function. It can take any value from negative infinity to infinity. That's the domain right here. All the values and all the x values that are possible to be substituted into the function. It's one way of explaining what the domain is. And then so now the range refers to the y value. So doesn't matter which input value that you're taking, and doesn't matter which form of your exponential function, but as long as we're looking at these basic ones right here, the range is anywhere between 0. It won't even hit to y equals 0. So the vertical spreading of our graph is always anywhere between 0 and positive infinity. So that's some explanations through the graphs about the domain and the range of any of our basic a to the x function. All right, and so at this point in our learning, then anyone viewing this video has already been clear that as long as we have a value being a positive value, then we can treat that as the base and define an exponential function just fine. So y equals a to the x is an exponential function, and the only requirements we need is that the base a has to be a positive value. And further, throughout seeing the different examples, then we are further even clear that the base didn't even have to be a whole value, but the base instead can be a decimal. And so just like that, think about the value that we have already known for so long, pi. In numerical approximates, pi is about 3.14, and this value has been, this constant has been introduced to any one of us since what, second grade, third grade, for calculating circle and area, circumference and area of circles. But now, strictly looking at in a numerical point of view, then this value is a positive constant, and it's a and as long as being a positive constant, then we can just simply define an exponential function just fine to be y equals pi to the x, just like that. And so my point again is to emphasize that anytime we having a value to be a positive value, and doesn't even have to be a whole value, in this case right here, a quite lengthy decimal, but we can already define an exponential function. And so this pi value being 3.14 is introduced to any one of us here in our learning since, as I said earlier, maybe second grade or third grade. But somewhere when we're starting to learn about in algebra 2, then we are being introduced to this e value, another known constant in the modern math. So similar to pi, we have another known constant to everyone out there that I'm about to show the value for this. Since I am going to skip the explanation of where this e comes from, then allow me to quickly switch over to my calculator and use the calculator to give anyone viewing the video here a numerical approximation of this e. So on my calculator, we can just simply, and the e to the x function is now quite simple. It's quite standard. So any calculator has a key somewhere to allow you to calculate base e raised to a value. And so here on the TI-8384, we have second e to the x right there. And so now that e is a constant, and to find the actual value, we can just simply give it exponent 1. And so now hit enter. So e to the 1 power equals e algebraically. And so now here's the actual value. Now I'm not saying that the decimal of e is ending at this last 8 right here. It's a lot longer than that. And this e here is a very lengthy decimal. It's an irrational value. But now at least anyone viewing this video has a picture of what that e value approximately equal to. And so now, as we have now seen, e is approximately 2.718 and a lot longer. But in the end, e is a value that's greater than 0, positive value. And it's a value that's also greater than 1. Simply being a value that's a constant, that's being greater than 0, we can just simply define just fine an exponential function with base e. Instead of base 2, instead of base 3, we can define an exponential function with base e, and the function comes out as y equals e to the x, where this value here is simply a positive constant. And so now y equals pi to the x is an exponential function, but it doesn't have it doesn't have too many applications out there, so not too many people worry about this. But e to the x, with this constant e being approximately about 2.718, slightly above 2.5, but this function e to the x has a large amount of applications out there, especially for people who are working in business field or the social and health sciences. And so And as we move on in the course right here, we will keep exploring the application of e to the x. But so now, strictly looking at this function as a mathematical function, as an exponential function in particular, then it's having a base value. Base e is a value that's greater than 1. Positive, of course, but greater than 1. So immediately after our study on the graphs of different exponential functions, then before I'm using my Desmos to pull out the nice looking graph, I can already expect that my graph, the graph for this function e to the x, is a graph that's rising one way from the left to the right. And it will rise more rapidly as the curve goes past the y-axis. And furthermore, I expect that the graph for e to the x will pass the y-axis at that point 0, 1. And so let's now look over to the graphing calculator with Desmos. And you can also use your TI-83 or 84 or any standard graphing calculator to achieve the graph of e to the x as well. But I prefer to use Desmos because it gives a really nice looking graphs with good precision for me. Alright, so on my Desmos graphing calculator, I have already prepared the function f of x equals e to the x. And so now I'm going to bring up the graph. And the graph comes out just as expected. It passes through my y-axis at that point famously known 0, 1. It's famous for not only e to the x going through it, but any other value, any other exponential function, basic exponential function will go through that point. And then again, it's a one-way graph that's rising from the left to the right. The rise, as you have seen earlier and have had some experience, the rise becomes more rapid when the graph passes the y-axis, and the rise is still slow when it's on the left-hand side of the y-axis. And that is what we know for now in terms of the graphing behavior of the e to the x function. And as we move on further into any study, we will find out more places where e to the x is playing an important role.